8:55. Steam enters an adiabatic turbine with 6 megapascals, 600 Celsius, and 80 meters per second. So you already know we're going to have to take into consideration kinetic energy. Then it leaves at 50 kilopascals, 100 Celsius, and 140 meters per second. If the power output of the turbine is 5 megawatts, determine the reversible power output and the second law efficiency of this turbine. Okay, so what we need to do, assume the surroundings to be 25 Celsius. This is crucial information, actually. Make sure I write my environment temperature here in the corner. T naught is 25 Celsius, or 298 Kelvin. Okay, so what do we know? What do we know? From everything we learned so far, we know that, okay, we're going from a higher state of energy to a lower state of energy. So that's why the turbine can output 5 megawatts. Okay, that's kind of the obvious part that we're already used to. So if we're going from the higher state of energy to our lower state of energy, this guy is going to be able to output 5 megawatts. Okay, but however, if we were to go into the isentropic down to the imaginary state, this guy will be able to convert more than 5 megawatts, right? Give us out more 5 megawatts. What is the difference between these two here? Well, the difference is the irreversibilities that we lost during the process. And these irreversibilities are related to the change in entropy, right? So this entropy that's being generated, it tells us that we're losing some energy that could be otherwise useful because of these irreversibilities. So let's start by talking about Exergy. Exergy is defined as psi, and I'm going to define the flow Exergy. Flow Exergy. Why is it flow Exergy? Because when we're dealing with a flow, you'll see why in a second, but when we're dealing with a flow, we know we have that PV term, the pressure volume term, and that PV term makes us consider enthalpy instead of internal energy. So our Exergy on any given state at any time will be my enthalpy minus my dead enthalpy minus my environment temperature, or my dead state temperature, and the difference between the entropy of my state and the entropy of my environment, or the dead state entropy, plus the kinetic energy that this guy has and the potential energy this guy has. Okay, so note this is just the Exergy of any given state. Let's try to break this guy down further. Okay, flow Exergy. Okay, so what are we talking about? We're talking about how much energy is available. Now, let's start by that concept, right? This is how much energy is available. And how much energy is available depends on our dead state, right? Our environment. So for the kinetic energy, it doesn't really depend on the environment. It's just a matter of, is it moving or not? Does it have a velocity? And if it does, it has kinetic energy. The potential energy is just a measurement of how far this guy is from the ground, right? So if we have any potential energy associated to it. But then the enthalpy, which is the difference from here to here, that's going to be related to what is our dead state, right? Because if we have steam at this guy here, the Exergy is going to be this guy minus the environment's dead state. If it's this guy here, it still has some Exergy related to the difference from the 100 and the 225, right? So it's the difference between the state that we're in and the dead state. Dead state temperature and the difference between the entropy that we have, the disorder that we have on our current state, minus the disorder that we have on our dead state. Okay, so first thing to know is that this equation relates to the Exergy of a flow at any given time. It's not in relationship to a process, it's not in relationship to anything. It's just in relationship to the dead state. Okay, so we're going to be using that guy there, and we're going to be using, obviously, the properties that we need to grab off the table. So let's start by writing down our properties. What is the first thing we're going to do? We're going to define our states, and you're going to go into the table and define them, and you're going to see both of them are superheated states. Okay, this guy's superheated, this guy's also superheated. You can check yourselves on the tables. Table A6 on page 910. I've grabbed my H1, and I'm also grabbing my entropy, S1. H1 being 3658.8 kilojoules per kilograms, and my entropy being 7.1693 kilojoules kilograms Kelvin. Okay. Other thing to note is, remember this Kelvin here? Note that we're summing up different units, right? Sorry, not different units, never different units. We're summing up different energies, right? So this energy here is in kilojoules per kilogram. This guy here, if we multiply by a temperature in Kelvin, we can get rid of this Kelvin. It's going to be kilojoules per kilograms. This guy here doesn't have the mass component, so this is joules per kilograms. We need to make sure to divide this by 1,000 to have kilojoules. And this guy, it's going to depend on what we're using. It's going to be given in joules, but we're going to eliminate this guy. So don't worry about it for now. Set of properties for the end state. So still on page A6, but this, sorry, still a table A6, but this time page 908. I've got the following properties. Enthalpy 2682.4 and 2682.4 kilojoules per kilograms, and entropy 7.6953. Okay, we have our properties. We're good to start doing some math. What are we being asked? We're being asked this guy here. What is this possible output that we can get, this work that we can get if we have a reversible process? Remember, the question is saying, what would be the reversible power output? So to be a reversible one, we have to have the same entropy just like before, blah, 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 blah. So what does that mean? Well, let's think about Exergy for a moment. Exergy on state 1, that is the availability of energy on my state 1, on this state over here, has to be equal to the availability of energy they have in state 2 plus whatever has been outputted as reversible work. This is all energy, right? All energy. So my Exergy on the first energy has to be equal to my Exergy on the second plus the reversible work. Now, look at this equation for a while, because it's not as trivial as it looks, okay? There's a lot going on here. This is only valid if we take into account the reversible work that's being outputted. Because if we were to look at this and use this 5 megawatt that is the actual work, we would have to write it like this. Exergy 1 equals Exergy 2 plus the 5 megawatt, the work actual, AC, okay? So work actual as in the 5 that's been released, plus any losses due to reversibilities. Okay, so we can look at these two guys in different ways. We're gonna go ahead and use this format here and expand upon this. And what you guys can do later is try to think of this way as well. We can solve thinking of it this way as well. Okay, this is the time that I need you guys to bear with me because we're about to do some maths. How much energy do we have on the first state? How much energy do we have in the second state? Let's go ahead and do that. So let's expand this guy using this thing here. So H1 minus dead state minus TO, S1 minus S of dead state, plus velocity 1 over 2, plus acceleration of gravity, height 1. Has to be equal to H2, H naught, T naught, S2, S naught. We might run out of space here. V2 squared gravity Z2 plus work reversible. O in energy. Okay, we're only talking energy. Missing 0.8 on H1. Missing 0.8 on H1. Oh, yeah. Thanks for that. Missing 0.8 on H1. All right, so if we send all these guys dividing, what are we actually doing? Well, we're getting the difference, right? The exergy difference in exergy from 1 to 2, which will be equal to our work reversible, which is what we're trying to find. Yeah? So what I can do is I can subtract these two monsters here. And then check it out what happens. We have a negative enthalpy naught, and then this is going to be a positive enthalpy naught. This goes away. We have a positive entropy naught, and we have a negative entropy naught over here. It goes away. Then, as long as my heights are similar, and we talked about this before, right? As long as this turbine is not ginormous, these guys are going to be the same. We can eliminate for them. Don't have to account for them. So this difference here will be H1 minus H2 minus T naught of S1 minus S2 plus V1 squared minus V2 squared over 2, which has to be equal to my reversible output, all in energy. Yeah, so far all in energy. Okay, what is next? Next thing to know is that we will actually want power out of this guy here. So we'd have to multiply everything by the mass flow rate. Okay, thankfully for us, there's only one outlet on that turbine, so all the mass flow has to be the same on both sides. So I can go ahead and do that if I want to now. But before I do that, I'm going to sub in the values that we have. Okay, let's sub in the values that we have. Difference between these two guys is just 3600 minus 2600. That's going to be 976.4. T naught 298. S1 7.1693. S2 7.69. Okay, this is going to be a negative, therefore it's going to be a positive. Start writing those down. 976.4 minus 298. That multiplies negative. Where is my negative? Here it is. 0.526 plus, mind you guys, this has to be 80 squared minus 140 squared divided by 2,000. All right, 2,000. Watch out, because we need it all in kilojoules. We don't put in kilojoules, we can't sum up things that are in different units. This ends up being our reversible output. Okay, and then finally this, I can go ahead and this is going to be 1126.55 kilojoules per kilogram, which equals the amount of work reversible. And I wish I could tell you we're done, but we're not, right? Because check out what we're being asked. Check out the answer that you have in your sheet. You want this guy in power. You want this guy in power. We're not satisfied with that guy in energy, in kilojoules per kilogram. We need to find a mass flow rate to be able to deal with it. And that's exactly where this guy comes in. Because if you think about it, we have this whole thing defined. We have the initial state, we have the final state, we have how much energy comes out. So we can use this information to be able to calculate the mass flow rate and then multiply this beautiful number down here to be able to account for the mass flow rate and transform this into power. So what I'm going to do now is I'm going to start a new sheet in which we're going to calculate the mass flow rate so that we can multiply mass flow rate on this side and have power instead of energy, mass flow rate on this side, so we can eliminate that kilojoules per kilogram and be left with kilojoules per second. Wait, why divide by 2,000? there was a 2 there from this beginning, right? 2 is there from the beginning, which is the kinetic energy. But we did this on the last class, so that's why I didn't go into it, right? Did it in the last class. The unit that we get out of this guy here is joules, right? Because it's kinetic energy. You do this, you look at the units, it's going to be meters squared over second squared, and that's going to be joule, right? That's going to be Newton's second law. Then these guys are kilojoules. This is kilojoules, this is kilojoules, because of these units here. Okay, so that I can sum them up, they have to be in the same unit. So I can't sum joules and kilojoules. It doesn't make any sense. So to be able to transform this into kilojoules, I've divided by 1,000. Yeah, brilliant. All right, so guys, screenshot time if you want to, because we're about to start a new page to find our mass flow rate. Okay, let's do it. New page. Okay, what are we doing in this new page? We're trying to find a mass flow rate. And how are we going to do that? Well, energy conservation, right? We did it 100 times already. You guys are sick and tired of doing it. You know how to do it. We have our first state here. We're dropping to a second state here. This guy's outputting 5 megawatts of energy, energy of power, I should say. And we can use all that information to calculate our mass flow rate. Since we know energy has to be conserved, what we can do is that the energy state 1 has to be equal to the energy state 2 plus whatever left our system. So let's just call this work output for now. Okay, and this is true because, don't forget, delta U equals Q plus W, and this guy goes away as 0. So all the work is related to the difference in temperature in the PV, which is enthalpy. Okay, what is our energy in the first state? Well, you know that already, right? It's H1 plus V1 squared plus gravity Z1, which equals second state. Enthalpy of the second state, velocity of the second state squared over 2, gravity, height of the second state, and then the work output. All in energy units, right? All in energy units on energy per kilogram. Again, Z is similar to Z, so we can go ahead and cross these guys out. You don't have to account for them. So that means that our work output there will be H1 minus H2 plus V1 squared minus V2 squared divided by 2. And that's going to be, again, we're going to have to do the same thing, right? To be able to account. As soon as we put in the numbers, we need to make sure they're all in the same unit. So as soon as I put in the numbers, I'm going to transform this into 2,000. This has to be work output. Okay. So this is the easy part. Now, what I want you guys to notice before we move on, okay, what I want you guys to think about before we move on is the following. Where's my previous page? Here it is, okay? If you note, the difference between what we just did, the relationship that we just found, and this one here, the difference is this term here, right? This is the novelty here. What is this term doing? This term is accounting for the irreversibilities of the process. Because if you look over here, this doesn't have that anymore. So what we could do is we could, instead of doing this loop that we're doing, we can actually use that difference there to be able to calculate the difference between the two work outputs, okay? And I'll tell you more about that when we get there. For now, what we need to do is we need to find our mass flow rate, because so far we still have one small issue here. This guy is in kilojoules per kilogram, and we don't know this guy. What we do know is the power output. And the power output has been given to us as 5 megawatts, right? It's not kilogram per kilojoules per kilogram. So what I'm going to do here is conveniently, there's two ways of thinking about this. We can take the derivative in respect to time for everyone if you want to, or we can just go ahead and multiply this by the mass flow rate on both sides. Because we know the mass flow rate of 1 equals the mass flow rate of 2, there's no change here. Every mass that enters my turbine eventually leaves it. And then you can think about this physically, which is taking the derivative in respect to time for every single one of these guys, or you can just do the savvy way, which is multiplying everything by m1. Okay, so I'm multiplying m1 on both sides of my equality, so they're not changing anything. And on this side, when we do that, when we multiply it by m1 as well, what we end up with is the power, right? Because if this guy was in kilojoules per kilogram before, and now we multiply it by mass flow rate, we get the power, which is one thing that we do know, right? Obviously, you could have worked this your way all the way down until you find the actual energy, and then use that to convert it back to mass flow rate. I'm just making our lives a bit easier by doing one step faster. This difference we already know. It's the same difference as before. This is the 976.4. This guy we already know as well. We already did before. That's going to be the 80 squared minus the 140 squared. And again, divided by 2,000, right? Because we need to account for that kilo in kilojoules, not in joules. Okay, all of this has to be multiplied by mass flow rate 1. And this guy here, now we know what this guy is, right? This is the power output, and now we know that is 5,000 kilojoules per second or kilowatts. Okay, so mind you that I also converted the megawatts into kilowatts. So they were all consistent here. Okay, so this is going to be, this math here is going to be a bit smaller than this because this is going to be negative, obviously. This is going to turn out to be 996.8. So my mass flow rate 1 equals my 5,000 divided by 969.8. And this is kilojoules per second. And this guy here is kilojoules per kilograms. Okay, so kilograms goes to the top, and then we have kilograms per second, which is what we're looking for. This is approximately 5156. Whew. Okay, now we're happy. We have our mass flow rate, and we have, from what we did on the last part of the problem, where is it? And we know that we have a reversible output is about 1,000 for every kilogram. So we can multiply these two numbers and have what is our reversible output. So let's finish it off. Let's write the way they're saying, what is the reversible power output? So reversible power output, that will be my 1126.55, 1126.55 times my 5.156. And this will be 5808.5 approximately kilojoules per second, which is the same thing as kilowatts, right? Okay, so let's finish off. That's the part A, and part B asks us what is the second law efficiency of the turbine. Okay, so this is part A. Part B is quite simple, right? Part B is what is the second law efficiency? If you guys remember, second law efficiency is related to how much we actually could get in relationship to how much we got. So our actual output in relationship to our maximum possible output. So in this case, my second law efficiency is, my actual is 5,000. Maximum I could get if I did it reversibly be 5808.5, which means I have 86.08% efficiency. Okay, so engineers have a leg room of about 15% to improve this specific turbine in question. Now, before we, oh, this is tilted, very tilted. That's better. Okay, if you want to take a screenshot, go for it. Now, before we finish off, there's 5 minutes to go. Okay, before we finish off, let's just think about what this is telling us. The actual output of the thing was 5 megawatts, and the reversible output would be 5.8 megawatts, right? So in other words, we're losing about 800 kilowatts due to these irreversibilities. This 800 kilowatts is accounted for in this term here, right, of our Exergy. The T naught minus S1 minus S2. So what you could do is you could use this term here to calculate how much is going to be the difference due to these losses of irreversibility. So you can go ahead, instead of doing the way that I did, what you can do is you can use this, only this term here, to calculate the 808 kilowatts. And that has to be the difference between your reversible process and your irreversible process, right? So I encourage you guys to first redo this whole thing. Let me actually stop recording.